Welcome to ZEISS Reverse Engineering, your software solution for surface reconstruction and tool correction. If you want to try things in ZRE, take a look at the description below. There you'll find links to download a trial version and training data. Since this video is a bit longer, let me point out that we provided chapter segments. Feel free to use them to pause the video, rewatch certain parts, or skip ahead. In this video, we'll create a cat for this small gear using standard geometries and a freeform geometry. At the end, we'll combine these geometries to create a watertight cat. To do that, I'll use a project where the scan data is cleaned up and aligned so we can start the surface reconstruction right away. If you're using a different project and need to edit your mesh or create an alignment, check out the video Edit and Align Meshes in ZEISS Reverse Engineering. Let's start by creating the standard geometries required for the reconstruction of this gear. We'll need 2 cylinders and 3 planes. To create these geometries, we need to select the respective parts of the mesh. If you watched the video Welcome to ZEISS Reverse Engineering, you might remember the selection tools in the toolbar. But selecting the outside of this cylinder, for example, might prove quite difficult with these selection tools. That's why there's a better way. It's called Best Fit via Dynamic Subselection. You can find the function in the action bar under Create from Scanning Data, Best Fit. And here's how it works. The first time you open the function, simply click a point anywhere on the mesh. ZRE then computes and stores the curvature values for your part in the project. That means that whenever you use this function again, the computation will be much faster, even if you close the function or the project in between. Now we can create the first element, a cylinder. As you can see here, you need to select points on the mesh. To do that, click a point on the mesh in the area of interest. You can also add regions to your point selection by using Control, but that's not necessary in this case. To select the entire cylinder, we need to adjust the parameters for subselection in the dialog. The dynamic subselection is based on curvature behavior. Here, you can choose between different types of curvature. I'll use the default mean curvature. Next, determine the type of element you want to create. In this case, that's a cylinder. And then increase the value here to add points to your selection. The selected points are highlighted in orange. Note that you don't need to cover the entire area with your selection. On the contrary, the dynamic subselection provides a degree of smoothing because, depending on the chosen curvature value, outliers can be excluded. When you're happy with your selection, click Calculate Best Fit Geometry to create the cylinder. When you look at the Model Explorer, you can see the created cylinder under Surfaces. Let's repeat this for the inner cylinder. Select a point and adjust the curvature value. The element type is still a cylinder. Now for functional part reconstructions, you can also define the cylinder axis and origin here. For more information about that, please check out our ZRE trainings. To create the inner cylinder, click Calculate Best Fit Geometry. Next, let's create the 3 planes. Select a point on the mesh, then change the geometry to plane. That's important. Increase the value here to select more points. And again, if you need to, you can define the normal direction here. To create the first plane, click Calculate Best Fit Geometry. And let's repeat this for the 2 planes surrounding the gear teeth. Now here you can see a great example of the automatic smoothing provided by the Best Fit via Dynamic Subselection. As you can see, the bump or imperfection on the mesh here is excluded from the selection, which means it won't impact the quality of our finished CAD model. For the plane on the bottom side, I need to decrease the value here because I don't want to include this area in my selection. You can use the mouse wheel or arrow keys to change the value in this field. Now we have 5 surfaces in our project, 2 cylinders and 3 planes. When you're working on more complex CADs, you may want to rename elements to keep things organized. You can easily do that by right-clicking the element and selecting Rename. Or you can use the keyboard shortcut F2. That's it for the standard geometries required for the reconstruction of this part. Let's hide them before we continue. Now let's look at how to create a surface for the gear teeth. Using the best fit biodynamic subselection won't work here because of the big curvature changes. Instead, we'll create a subset of the mesh for the gear teeth. This is where the selection tools in the toolbar come in. To make your selection easy, consider your viewing angle of the mesh. To best select the gear teeth, we should use a straight frontal view. Because the gear is aligned, we can use the coordinate cube to adjust the view with a single click. To select the gear teeth, activate Subselection in the toolbar. Make sure that Subselection All is active. That means that you select everything in the selection area, not just the front of the mesh that you can see. Then use Ctrl and the left mouse button to drag a rectangle and select the gear teeth. Be careful not to select too close to the edges, since they feature fillets. If you made a mistake and want to start over, you can clear the selection here in the toolbar. In case you're wondering why I'm limiting my selection, it's because I want to show you how to extend surfaces later on. You could select a larger area here, just stay away from the edges. Next, double-check your selection. To do that, hide the mesh and look at the area you selected. As you can see, I also selected the cylinder in the center because I selected all the way through the part. But that's not a problem. Simply deselect the cylinder. To use the lasso selection, use Ctrl and the right mouse button. To create a subset of the mesh based on the selection, click the plus in the toolbar. And here's the subset in the Model Explorer. Since we're done with the subselection, deactivate it in the toolbar. If your cursor shows this little stop sign as you continue, it's likely because you didn't deactivate the subselection. For most commands, you need the element or geometry selection. Now we can use the subset to create a surface. To do that, we'll use the function surface approximation to points. If you watched the video Reverse Engineering for Rapid Prototyping, this may sound familiar. Select the subset either in the CAD window or the Model Explorer. Then choose the projection type Cylinder. Now our starting surface for the approximation is a cylindrical surface approaching the point cloud with every iteration. In the center of the cylinder, you'll see a yellow arrow. Let me hide the coordinate system so you can see it better. The keyboard shortcut to hide it is Ctrl-0. This arrow indicates the cylinder axis and origin. It must be in the center of the cylindrical surface. If it's not, you can change the orientation and position with these parameters here. But in this case, it's fine. Now for the segmentation. V always represents the segmentation in axis direction of the cylinder. U, the segmentation perpendicular to that direction. Choose U and V different. Then determine the number of segments in each direction. The gear has 14 teeth. Whatever number you choose for U, multiply it by 14, so each tooth is represented by an equal number of segments. I'll use 15 times 14. As I said, V represents the segments in axis direction. Here I want to prevent curvature, so I'll use one segment and lower the degree to 1. That ensures a planar connection in V direction. Then click Execute and Close to create the surface. As you can see, throughout the 20 iterations, the distance between CAD and mesh is minimized. Let's check what the actual deviations are between the mesh and the created surface. Open Analyze, Distance Analysis, Nominal Actual Comparison. As reference element, select the surface. And under Actual Data, select the subset we created, which you'll find in the Model Explorer under Points. Change the accuracy to user-defined and click Analyze. And as you can see here, we get a tolerance of about 30 microns. For more information, look at the information window. It shows the number of points, maximum and average distance, as well as standard deviation. The deviations are very uniform throughout the gear teeth. Any idea why? What you're seeing is actually the wear and tear of the gear teeth. That means that our created surface better represents the original state and has a higher quality than the scan data. Feel free to adjust the tolerance and create a snapshot for reporting purposes. Once you're done, you can close the function. Now we have all the individual surfaces that make up this part. But in order to create a CAD model, we need a watertight body. As you can see in the Model Explorer, we currently don't have any bodies in this project. Step 1 is to check if the surfaces we created intersect. You can use the highlighting in the sub-toolbar, or simply add transparency to all the elements to get a better view. Good news is, all our surfaces are intersecting, except for one. The freeform surface for the gear teeth is too short. It should be intersecting these two planes. But that's an easy fix. Simply use the search function in the action bar and type extend. We want to extend a surface, so select Extend Surfaces Bodies. Up here, you can see the function path, Edit Extensions. Just a little side note or reminder, you can add functions that you use frequently to your bookmarks for quicker access. In the function dialog, you see what to do next. Click the boundary curves in the CAD window. We want to extend both ends of the surface, so I use Ctrl and the left mouse button to select them both. Now you can use the blue handle to extend the surface, or change the value under extension distance. The new boundary curves of the surface are shown in yellow. Click Execute and Close, and let's check again. Now you can see that the freeform surface intersects the plane on either side. The next step is to combine the surfaces. This will result in a body. To do that, either use the search function and type Combine, or open Create with Elements, Boolean Operations, Combine Elements. Select all the surfaces. The easiest way to do that is to select the category Surfaces in the Model Explorer. And if you want to keep the auxiliary elements you created, untick this box. Otherwise, they will be deleted. Deleting them makes for a tidier Model Explorer, but you lose the ability to retrace your steps. Click Execute and Close. And here's the newly created body. Let's hide the surfaces and display the body exclusively. This body doesn't really look much like the mesh we want to reconstruct. Too much excess material around the edges. Now we could select all the geometries that need to be deleted manually, but there's an easier way. In the action bar, under Create with Elements, you'll find Derivations, Extract Solid Body. Now click on the boundary surface of a solid body, the plane on top of the gear teeth, for example. The software now displays a yellow arrow. This arrow must point away from the material. If it's pointing towards the material, click the yellow arrow to correct the orientation. When you click Execute, the ZRE software checks in the inverted arrow direction, looking for an enclosed volume, and creates a new solid body. Let's hide this body to see the new solid body we just created. Now all that's missing is the top cylinder. Display the other body again, select the cylinder, make sure that the yellow arrow is pointing away from the material, then click Execute and Close. This looks a lot more like the mesh. However, we still have two separate bodies. To get one watertight body, we need to unite them. Open Boolean Operations and select Unite Elements. Select the two bodies we just extracted with Ctrl and the left mouse button. In this case, I'll automatically delete the input elements and click Execute and Close. And now we should have one single watertight body. To make sure we didn't miss anything, let's perform a check. Open Analyze, CAD Analysis, Volume of a Body. Click Calculate, and if you created a watertight body, the software calculates the volume of the body and displays the result in cubic millimeters here. If you get an error here, that means that you might have gaps or overhang, or that curves belong to more than one surface. To investigate further, you can use the edge analysis. For more information about that, take a look at the user guide or check out our ZRE trainings. Now we're almost done. We created a watertight body from our mesh. But can you see what's missing? Look at the details, the edges to be more specific. When we compare the mesh to the CAD, you can see that the mesh features fillets and chamfers. Here's how to create them. Let's start with chamfers. Open Edit in the action bar and select Fillet and Chamfers Chamfer Edges. Now the easiest way to create chamfers is to set the CAD transparent and display the mesh in the CAD window. Just so you know, you can also change the display color of the mesh under Settings, Visualization, in case that makes it easier for you. On the CAD model, click the edge you want to edit. Use the blue handles to adjust the width of the chamfer. Click Preview to see what it would look like. If you make adjustments and the preview disappears, click on Preview again. This is not a software issue, it's due to your graphics card. If you're happy with the preview, switch to Angle and Distance in the dialog. Here you can enter precise values. I'll change it to 1.6 and 45 degrees for the angle. Click Execute so we can create another one on the bottom. Adjust the position of the CAD model in the CAD window. Remember, right mouse button to rotate, left mouse button to move. Select the edge, switch back to Distance, Distance, and adjust the blue handles. Adjust the values under Angle and Distance, and then click Execute and Close. Now let's create the fillets. Select Fillet Edges. Click on the edge you want to edit. The preview you see in yellow is only a rough preview at first. To get an even better view of the fillet edge, hide the CAD in the Model Explorer. Adjust the radius. Then click Preview to see a more detailed preview. When you're happy with the result, click Execute so we can continue with the remaining fillets. Repeat this for the bottom edge of the cylinder. Hide the mesh to select the edge. Display the mesh and hide the CAD. Adjust the radius. And create the fillet edge with Execute. Now there's two edges left, the top and bottom of our gear teeth. Select the edge. With this edge, you can really see that the quick preview is skewed. Click Preview to fix it. If the preview disappears, meaning the purple lines and yellow surface are no longer visible, your radius is too big. Decrease the radius and click Preview again. And here it is. Click Execute and repeat this one last time for the bottom edge. And that's our finished CAD model, composed of standard geometries, a freeform surface, and complete with fillets and chamfers. To export it, select it and click Export Geometries. Export only the selected elements. Choose a file format and you're done. If you want to dive deeper into the world of ZEISS Reverse Engineering, take a look at our trainings. You'll also find links to more content and other ZRE videos in the description below.